Hello, hello, am I audible? Hmm. Hello,
Yes, wait.
hello, Jerry.
Hi, sir. Let's go. Sorry for the delay here. Let's go.
No, no problem. I'll just share my screen.
Yes.
Is the screen visible?
Oh, yes, it is visible. Yes.
Okay. So before we start with today's lecture, I'll just tell you the roadmap how we are going to go about. And today we'll be
Okay.
completing the expectation that was from me. So basically,
Yes.
we will just have a quick revision in 5 to 10 minutes about what we
Yes.
learned today. Okay, because this
Yep.
thing is
Yep.
important
Yep.
to solve all the problems that we are going to do today. Okay.
Okay.
Along with that,
Understood.
then once we are completed with that, then there are some pre-lab questions. One, two, three,
Yep.
4, 5, 6,
Yep.
7. Around there are 8 to 10 problems which are there over here. We'll be solving all those problems because these problems are purely dependent upon what we learned yesterday. Okay, there is nothing dependent on experiment as such. Hence, they are pre-lab questions.
Okay.
Okay, post that, this is
Okay.
part of experiment which you'll be performing in your labs. What I will be doing is that I will be just taking one of the examples from this, like beta one, and they asking you to find out the carrier P, first band, first parasite one. So I'll just solve for you one thing so that you have an idea. And when you do it in your lab, it will be a little easier for you to interpret. Okay. Then
Absolutely.
about the demodulation of FM signal, I will be explaining you this entire PLL process, which is there. I'll explain you this thing, how is it that, because here they have only given you the diagram, nothing more than that. So I'll explain you the theoretical concept of it so that when you use all this FFT function and everything, you'll be able to better understand. And your college professor will be teaching you on the thing. Again, over here, this
Yes.
is
Yes.
purely based on experiments. So I will not able to take this part of the values, but definitely I'll teach you about the performance comparison between the wideband and the narrowband, and later on with respect to amplitude and frequency modulation. So that will be it from
Okay.
my side.
Understood.
So let's get started.
Yes.
Okay. So any issues with my teaching yesterday? You didn't understand something? Any problem? I should change some methodology of
No.
mine.
No. 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 Really, sir. It's good, sir.
Okay.
It's good. I'm
Okay. Fine.
happy with it.
Okay, fine. So let's begin. So what we learned yesterday first is modulation. So modulation is the technique
Yes.
in which one of the characteristics that is very important because there are many characteristics of a carrier signal like amplitude, phase, frequency. So only one of the characteristics will vary with respect to instantaneous change in message signal. That is called as modulation. So what happens?
Yep.
I have a message M of t. I have a carrier signal C of t. So depending upon my message signal, any one of these characteristics will be varying with respect to M of t. Hence, it is called as modulation. This can be a sinusoidal, this can be cosine, it can be different kind of waves. But the
Yes.
concept is that the carrier signal will always vary with respect to amplitude or frequency or phase with respect to the message signal. That is modulation. Now, modulation also involves the basically the conversion of lower frequency to higher frequency. This is a very layman definition, I will say. So this is basically lower to higher frequency kind of process. Hence, what happens is that if I consider this C is equal to lambda F, lambda is equal to C by S. As my frequency increases because of this, my lambda value reduces, which helps me to keep the value of my antenna lesser, which again helps me cost-wise, very cost-effective. Then we learned about the first kind of modulation, that's amplitude modulation. I've not gone in depth in this because the requirement was frequency modulation. If required, we can take it later. What is amplitude
Yes. Yes.
modulation? Amplitude modulation is the process in which the amplitude of the carrier, as I told you, there can be amplitude, there can be frequency, there can be phase. So here it is amplitude. So amplitude of the carrier signal varies with instantaneous change in message signal. So I give you an example. Remember this, you know, standard definition of denoting M of t and C of t. M of t is equal to
Yes.
AM cos 2 pi FMT. C of t is equal to
Yes.
AC cos 2 pi FCT. The cos and
Yep.
sine can differ depending upon the phase. And your AM is the peak value. And if I talk about this complete thing, that is the peak to peak. Generally, AM is equal to peak. Similarly, your AC is your peak value, PT, and this is the peak to peak value. That is important.
Okay. Okay.
Post this, your carrier signal, as I told you, will always, the amplitude will always change with message signal. Therefore, you can say AC is directly proportional to M of T. AC is equal to K into M of T, where Ka can be told as AC by M of T, and your Ka is defined as amplitude sensitivity. Always mention which kind of
Yes.
sensitivity. Don't just mention sensitivity. It can be amplitude. Then we learned about KF, which is the frequency sensitivity. Then we learned about KP, which is a phase sensitivity. So mention the kind of sensitivity it is. I told you a diagram of amplitude modulation in which we had the signal M of T, we had the C of T. So depending upon the amplitude of the message signal, my amplitude of the carrier signal went varying. When the message signal amplitude was higher, the carrier signal amplitude went higher. When the message signal went lower, the carrier signal also amplitude varied. So it's directly
Yep.
proportional to the message signal. Then we learned about angle modulation. Angle modulation can be
Yeah.
of two types, the frequency and the phase modulation. This is the
Mhm.
standard, carrier signals, C of T, AC cos 2 pi FCT. Okay, where what happens is that your phi of C is equal to M of T. And
Yep. Yep.
let's say phi is equal to Kp into M of T, where Kp is the phase sensitivity, where Kp is given as radian by volts. You need not, remember it. Just remember this particular statement. Automatically, you'll be able to write Kp is equal to phi c upon M of t, which is phi is a phase kind of thing. Hence, it is radian. M of t is volts. So you need not remember this. My aim to you in teaching was
Yes.
that to try to simplify as much as I can, because there are already a hell lot
Yep.
of things for you to remember in communication. So if you can remember some things and something you can always derive. It's not possible to by heart and learn everything. Next, we have frequency modulation.
Yep.
So frequency modulation was something that was expected. So
Yep.
we went into deep into this. Frequency modulation is a process or a technique in which the frequency of the carrier signal varies instantaneously with respect to that of your message signal. So it was CT is equal to AC cos 2 pi FCT. FC is equal to KF into M of T. That is kf is equal to hertz per volts. Now, the standard
Yep.
expression, of FM signal is given as this. Over here, S of t is equal to AC cos 2 pi FCT plus 2 pi kf integral minus infinity m of t dt and AC cos 2 pi FCT plus beta sine 2 pi FM. These are the standard signals of FM, irrespective of narrow bandpass or wide bandpass. Then we learned frequency deviation. Del f is given as kf into am, and the beta is given as del f into fm. The beta is given as del f into fm. That is very important. Then, depending upon beta, which is the modulation index in frequency modulation, beta is divided in two types. One is the beta smaller than one is the beta greater than 1. Greater than equal to 1. So when beta is smaller than 1, it's called as narrow bandpass FM. When beta is greater than 1, it's called as wide bandpass FM.
Yep.
This is the standard mathematical expression for your narrow bandpass FM. AC cos 2 pi FCT plus beta AC by 2 cos 2 pi FC plus FM into T plus cos 2 pi FC minus FM into T. Okay. Then you
Yes.
had the spectrum, which we drew just on the basis of this equation. Then two important formulas, bandwidth of a narrow bandpass FM is given as 2 times FM, which you can see over here. And PT is equal to PC into 1 plus beta square by 2, wherein your PC stands for your carrier power and PC beta square by 2 stands for the sideband power of both these sidebands. And
Yep.
if you want to know for individual sideband, just divide by 2. That is the concept. Then for wide bandpass FM, we always use Bessel's function, that is Jn of beta. So
Mm-hmm.
as the n value keeps on increasing, the Jn beta value will keep on reducing. We have certain
Uh-huh. Uh-huh.
properties of Bessel. We have certain properties. Anything you want to ask?
No, not really. Okay, I understood.
Okay.
Yes.
Okay, so this is basically the Bessel's function. Then we have the modulated mathematical expression for modulated signal of a wide bandpass FM as summation minus infinity to infinity for n AC j n beta cos 2 pi fc plus or minus n fm into t, where n indicated the
Yep.
number of positive side bands. Very important. Then we had this diagram which we drew. Then we learned about Carson's rule, wherein we had the bandwidth as either 2 NFM or according to Carson's rule as 2 into beta plus 1 into FM. And the power was told
Yep.
as PC is equal to PC for all values except beta 2.41, 5.5. And when the values of beta is 2.41 and 5.5, that time the PT is not equal to PC but equal to PF. So this is the basic that we learned yesterday. Any doubts till here, Jerry?
Yep. Not really, sir. You're quite clear, sir. Yes.
Okay. So now we'll try to
Yeah.
take up the problems. You can also open this PDF
Yeah.
on your laptop if necessary, and we'll try to solve the problems one by one. Okay.
Yep. Yep.
Okay. Okay. So let's try to, first jot down all the values that are. Okay. If you see, the question says a 4-volt peak to peak 100 kilohertz carrier. So if you know what they are saying, in the question is 4-volt peak to peak and 100 kilohertz carrier, right?
Yes.
So it means they are giving information about the carrier. Okay. So AC is going to be 4 by 2 is equal to 2 volts. Why? Because I told you very clearly, AC is just the peak value, if you remember.
Yeah. Yes. So two is the V peak, the peak value, not the peak to peak.
Yeah,
Yeah.
VP,
The
I
V.
told you,
So the peak.
your AC is equal to VP. Hence,
Yeah.
peak
Understood.
value is not required. Okay. However, you can check this problem when it's taught to you in the university also in your college, and you can get a better perspective about it. Okay. Generally, AC is equal to 4
Yeah.
by 2,
Yeah.
that is 2 volts. Okay. The next thing they're
Yeah.
saying is
Yeah.
carrier frequency, that is FC is equal to 100 kilohertz, right?
Yes.
Okay. What is the next thing they're given? a 4-volt peak to peak 100 kilohertz carrier is modulated by, what do you mean? Who will modulate? The message signal, correct? A carrier signal is always modulated by a message signal. So it's modulated
Message.
by
Okay.
10 kilohertz sinusoidal signal. That means what? The M of T is given as the frequency as 10 kilohertz and FM. And we know that FC is always greater than FM, which can be verified from here. This is 100 kilohertz. This is 10 kilohertz.
Oh yes, so the FM is 10 kilohertz. Yes, so it's much
Okay.
bigger. Yes,
Please
correct.
do not get confused with the notation because here they use the notation for M of T as S of T. Generally, for modulated signal, we use S of T, right? For message, we
Yes.
use M of T. For carrier, we use C of T. And for modulated
Yes.
signal, we use S of T. But here, they use different
Yes.
notation. So you need not get confused. Just understand
What do
the
you mean
meaning
different?
of the
What
term.
do you what do you mean they use different notation? It's the same, isn't it? It's a SC SLT, isn't it?
Yeah, see, what they're telling here is modulated by a 10 kilohertz sinusoidal signal S of T. So here they have used for message signal the notation S of T.
Oh, okay. The message signal is SLT. So, okay.
So the notations can differ, Jerry. That you don't worry. What is important is that you have to realize the question and the language of the question. So the question
Yes,
said
yes. Sometimes.
it is 4-volt peak to peak and 100 kilohertz carrier. So what did I do? I found out the attributes of carrier, AC and FC. Then it said that modulated by 10 kilohertz sinusoidal signal. So when I talk about modulated by, that means message signal. You need not refer the notation. Therefore, M of T or S of T is going to be 10 kilohertz. And FC is much greater than that of FM.
Yes.
Any doubts till here, Jerry?
No, it's clear,
Okay.
sir.
Okay. To produce a FM signal of X FM of T. Now see what they have done. To, instead
Uh,
of I'll say giving modulated
SLT.
signal S of T, they have given us X FM of T.
Yes.
Yes. So just they have changed the notations. That is okay. You need to know the meaning. With the modulation index as beta is equal to 1. So what they're saying
Uh,
that the modulation
it's
index beta is equal to
it's
1.
wideband, right? B equals to 1 is
Yes,
wideband,
correct.
right?
Yeah. Okay. So what happens is that they've given the value of beta as 1. Now what
Yeah.
is happening is that now imagine Jerry, they would have not given you notation beta. They would have just given you which modulation index is 1. Then you should know that this modulation index is nothing else than beta.
Uh-huh.
Okay. So in the exam, they might not give you the notation, but you should know that the modulation index is denoted by beta. Okay.
Okay.
And the frequency sensitivity is given as
Clear.
F, which is equal to 10 kilohertz per volt.
10. Yeah. Yeah.
Answer the following question. So is the data clear, Jerry? What data is given to you in the question?
Oh, yes, it's clear. So it's basically I
Oh,
just copy the thing. So I say AC cosine 2 pi FC T
okay.
plus beta sine 2 pi FM T. Is it something like
Excellent.
that?
Excellent. So I'll just solve and show you. Okay. See now if you remember what we learned in the two standard definition, if you remember some time back. Here is it. These are two standard definition of your FMT. Either you use
Yes.
this, either you use this. So we'll try to use this. Okay. So what
Yeah.
does this equation say? So don't use the word S of T now. Now use the word X FM of T. That's the question. Okay. So it is
Okay.
AC
Okay.
of 2 pi FCT plus beta sine 2 pi FMT. What is AC given as?
Oh,
2
wait
volts.
up. Beta sine 2 pi FMT, and then it's 2
So what
cosine.
is FC given as?
FC given as
FC?
100 kilohertz.
What is beta? 1.
Yes. Yep,
FM
1,
is
and
given
then
as 10
sine
kilohertz.
2 pi times 10k t.
Any doubts in this?
No, it's good. It's good, sir.
Okay, now
It's
see,
good.
here we just use
Understood.
a general equation. So the thing that you asked me whether it's wideband, narrow band pass, it didn't matter over here because
Oh,
we
really?
use just the FM signal, irrespective whether it is narrow band pass or wide band pass. So in the question,
Okay.
anytime you get confused, don't get worried. Just try to use the general equation because that is applicable both for narrow and wide band pass. Am I clear?
Narrow band, wide band. Yes.
Okay, so I hope now you're understanding, Jerry, what is happening in communication and frequency modulation. Yesterday, you told me that everything is going a bouncer for you, not able to understand. But today, are you able to
Yeah.
understand?
Yes. It's so kind of I know have some direction of it. Good.
The next question. Now let's try to take the next question. Okay, it
Yes.
says use Carson's rule to determine. See, as soon as they use the word Carson's rule, you should realize this is a wide band pass signal because you know that
Okay.
Carson's rule is applicable only for wide band pass, not for narrow band. Correct?
Okay. Yep.
So use Carson's rule to determine how many significant sidebands in the spectrum of FM signal must be considered. Explain. So how do we solve this question? Okay. So what happens is if you see, wait, I'll just do one thing. Okay. So what happens is if you see,
So something happened. A glitch.
yeah. Please give me a minute. I'm sorry for
Yeah.
this.
It's okay.
Please. Okay, so we learned this thing, right?
Yes.
Okay. So after that, now the question says, please find out the number of sideband using Carson's rule. So if you remember,
Yes.
what did we learn the bandwidth as in Carson's rule? The bandwidth in
Bandwidth.
Carson's rule is given as 2 into n into Fm, correct?
Yes.
And it is also given as 2 into beta plus 1 into Fm.
Wait, let me see. Where is that? Where is that? Yeah, okay, yeah, something like that. Yes, Carson's rule, 2 plus beta 1 times FM. Correct. So correct.
Yeah. So what happens is that can we equate this both because this both are equal to each other because they indicate the bandwidth of a FM signal. So I can say
Yes, but you have to use the Carson rule, the lower one, isn't it? The 2 beta 1 plus beta plus 1, and then times the FM because it is
so we can just cancel this 2 and F1. N is equal to beta plus 1. Do you agree?
okay, understood. Wait, so let me jot this down. This is kind of important. The years. Okay. We can play around with this. Yes, so let's go.
Yeah, so this is basically N is equal to 2. Hence, answering the question that is mentioned over here, how many thickness sidebands mentioned very clearly, there are 2 positive sidebands on the
Yes.
positive end. And if we consider the negative part, it will be 2 plus 2, 4. So depending upon what is expected, you can write. So this thing will be solved also in college also, so you can try to understand better that. Okay.
Mm-hmm.
Okay. So now what is the next question? Next question is basically 98% power bandwidth and the power of the modulated signal. Okay. So there are two things. 98% of power bandwidth and the power of the modulated signal.
Yes.
So when they say 98% power bandwidth, Jerry, right? You need not
Yeah.
get confused at all. It just means the bandwidth only, nothing different. And what is the bandwidth given as? 2 into beta plus 1 into Fm for by Carson's rule for a wideband pass FM. So 2 into Fm, 10 kilohertz. Is this right,
Mm-hmm.
Jerry? Any
Oh.
doubt over here?
Wait, bandwidth. Modulated the signal, so it's message signal, so it's
So
10
just
kilohertz.
remember the bandwidth of a modulated signal is given as 2 into beta plus 1 into Fm. If you remember what we learned
Yes.
over here, I just showed you, right? Either you use
Yes,
this,
yes.
either you use this, any one of them, since it is a wide band pass FM, beta greater than or equal to 1. Hence, I
Yes,
can
yes.
use this formula and I can find. Any doubts in this, Jerry?
No.
Okay. And feel free to interrupt me if you feel anything is done wrong. Okay.
No, I understood. I understood.
Now they ask the transmitted power of the modulated signal. Okay, is the second thing. That is PT is equal to. Now, if you remember, what did we write over there, Jerry? In case of wide band pass SM, PT will be equal to PC for any value of beta. Any
Okay.
value of beta except 2.41 and 5.5. And it will be equal to PSB for beta is equal to 2.41 and 5.5. Right? Now, what is my beta value over here?
Uh-huh.
1. So I can use this formula, right?
Uh-huh. Yes.
So PT is equal to PC. PC is always given, I told you, AC square by 2R. What is the value of AC? 2
AC
volts.
is amplitude 2, yes.
So 2 square upon 2 is nothing given for R. So we can assume as 1. Hence, it is
Oh,
2.
really? So, oh, okay. Wait.
If in the college they end up giving you some value of R, when you're solving this lab question or in your exam, whenever, you can always substitute the value. If not given, you can assume it as 1.
Wait.
Yeah, please take your time.
Expect of V of V X 走才呀。Yeah. Let's continue. Let's go, sir.
Yeah. Okay. So did you understand this? Now there's one more part to this, Jerry. That is the in-band power ratio. If you're able to see this thing, in-band power ratio. This is something that even I need to check. Okay. Right for now, I'll admit that I don't know this part in-band power ratio. I'll let you know. I need to check this part.
Yeah.
Okay. But all other parts I've taught you properly.
Well,
Okay.
why you have to check the band power ratio, sir?
What you're saying?
Are you, so why are you not teaching me the second part? Are you uncertain about this, or it's
I'm a little uncertain about this. I'll let you know. Okay. About this in-band power ratio.
okay? So answer later
Okay.
on, or what?
Yeah.
So you answer this. Why is that, sir? You not confident with this part, or it's
No. I will just have to find out this thing. because this is something new term even for me
Okay.
also. So I'll let you. Okay, I didn't want to just miss it. I wanted to
Oh, it's
inform you.
okay. So you no, right now you're not certain about it, so we skip this part. Okay, it's okay.
Yeah.
So,
Okay. Fine. Now the next part is name the three FM signal demodulation techniques. Of course, there are many demodulation techniques. They only asking you to name over here. So they have told you find the three techniques from the textbook, which they mentioned over here. So if you have the textbook, you can refer that particular textbook, and we will give you, the three demodulation techniques. However, the ones that I am aware about, I'll let you know those names. Okay, and you can also refer the textbook, the names that they mentioned over here, right? Find from the
yeah,
textbook.
yeah.
That is, you can refer that. Also, I can tell you from my side, there are different demodulation techniques which are there. FM demodulation techniques. FM demodulation technique. What do you mean by demodulation, Jerry?
Yes.
Can you tell me?
Demodulation is a technique in which one of the characteristic
Demodulation,
of
not
carrier signals
modulation.
varies with. Oh, demodulation. Demodulation is demodulate, isn't it? It's like how do I put it? It's like you you receive the message signal and the carrier signal. You get rid of the carrier signal. You only have the message signal. It's called the
Correct. Yeah.
demodulation, isn't it?
Yeah, somehow you can say. I'll tell you in simple words what does it mean demodulation. Okay.
Okay.
We have a M of T, right, in modulation. It goes through
Yes.
something and you get S of T.
Yeah.
That is a modulated signal.
Yes.
So demodulation is just the opposite of it. The S of
Yes.
T will go through some process to get M of T.
Yeah.
Clear? That is simple
Yep.
demodulation. Now, as I have told you, there are different techniques which is mentioned in your textbook, which you can definitely refer. I will tell you the technique that I am aware about. I'll just name those techniques because they have
Okay.
just asked to name the techniques. Okay. One,
Okay.
there are two ways. One is frequency discriminator. Is the slope detector.
Oh, okay. Is it like coherent detection? Oh no, that's for the AM. That's AM probably.
So here they have just told you to name it. So I'm just naming them.
Yeah.
You can
This
also
was
refer the
balance.
textbook. Yeah, balance
Balance.
slope detector.
Okay.
And then the most important part in phase discriminator, which I'll teach you later on, which I told you also,
Okay.
is
Okay.
the PLL. Because
PLL.
PLL diagram is shown over there. That is the phase lock loop.
Yes. Phase lock loop.
Has this thing been taught in your college?
Yeah, something like that, sir. Something like that. PLL. Yes.
Okay, so
So
what I want to tell you is that
it's very very unclear. He goes through these things. He just bombarded with all this information, and then we cannot absorb. It's all those kind of things. You know what happens. Once the time you're a student, you get overwhelmed. This will happen.
but I hope that after I have taught you, it's not the same condition, right? You understood
Yes,
something.
yes, 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 yes.
Okay. So these are the techniques. Always you can refer the textbook that's given to you. There can be many other techniques which they might have mentioned. So, but this is the one that I am aware about. There can be many others. Okay. About phase
Yep.
discriminator, I will teach you. Okay, later on. Now the next part. Okay. So now the next part is another set of questions. So are you ready to solve this question, Jerry? Or you want a break?
No, yeah, so let's go.
Okay.
Wait, so can you move up a little bit? Move up the question. Can I see the question again?
Yeah.
No, can I see the question paper? Question paper. Can you scroll up? Scroll up. Yeah. Oh, okay. So basically, so the technique I can just Google it, right? You give me the
Yeah,
O3, I
yeah.
just Google. We
Yeah.
can
Or if they've
no
given
waste
some,
of.
yeah, or if they give you some techniques, you can find out from that also. If they give
Okay.
any textbook or something, you can find out from that. But you're just told to
Yeah.
name the three FM or the three techniques. Just
Okay.
name. There are many.
And then these three techniques are universal, right? The name are the same. You cannot be any other
Yeah,
names, right?
but it's better that you refer your textbook also, what is given to you,
Okay.
because it's just many, and there
Okay.
are so many techniques, to each process. There can be so many techniques, can be subjective. Okay.
Okay. Okay. Yeah. So let's go. Let's go to the next
Yeah.
one.
Yeah. So the next one is basically, so see, why am I able to solve all these questions, Jerry? Because these questions are not lab dependent. It doesn't require any kind of instrument or something. Further on, the questions are lab dependent, which cannot be
Yes.
solved away. That can be only solved when you do the things in the lab on the oscilloscope and everything.
Yes, absolutely.
So,
Of course. Of course. Of course.
so,
Of course. So I think
what are the,
you should receive two pictures from the guy. Is you see the oscillator and the
yeah,
TMC the
but
T
even if you send me, right? Even if you send me, right? It's only when you perform it practically, you will be able to see the waves
yes
and
yes
everything
yes
proper.
yes
Okay.
yes yes yes
It's just
yes
an instrument.
absolutely
Okay. But
absolutely.
I can teach you the theoretical part of it and I can solve numericals. But the
Yeah
ones which are to be done in the lab,
yeah
they
yeah
can just be done in the lab. Okay, that's clear.
sure yeah yeah
Okay, so let's try to solve the next question. One, the next
yeah
question says an FM signal X FM of T. So let's try to. So always, Jerry, when you get a question, right, please try to write down the data which is given. It will simplify the question for you.
yeah
Okay, as you keep reading the data, please keep on writing. As you keep reading the question, keep writing the data. It says a FM signal X FM of T. So they are giving you information of XM of T. Is produced by modulating a. So what is getting modulated, Jerry? Carrier or message signal?
modulating is message, isn't it?
No,
Oh wait
it's produced by
wait modulate
modulating a.
carrier.
Okay, see, so please understand the
Carrier.
English. The carrier signal is modulated always.
Okay.
Okay, or modulating whatever. A
Yeah
message
yeah
signal is the one which will modulate. So understand what is given the question. They might not give as C of T, S of T, M of T, but they'll give you this. So it's produced by modulating a 4-volt peak to peak. That means what? They're giving the value of AC, right? AC is
yes
equal to 4-volt peak to peak, which is equal to,
two.
sorry, it is basically peak to peak by 2, which is 4 by 2 is equal to 2 volts. Any doubts here, Jerry?
No no. So this is a carrier. Okay.
Carrier. Along with 100 kilohertz carrier. So
Yes.
FC is given as 100 carrier. Now see, Jerry, what happens over here? Even if you get confused in the paper, just try to see the value of FC.
Oh yeah. I saw that. I saw that.
The
I was
FC
like, okay,
value,
this frequency very big, you know?
yeah, it's a big enough frequency, right? So even in the question you get confused,
Yeah.
just try to approximate. Okay, this frequency, so this will be of carrier. Okay, sometimes the question can be confusing, so don't get confused. Okay, so the question says it's produced by modulating a carrier with S of T is equal to this. What is this S of T, Jerry? Is it M of T or C of T?
The modulating with modulating of the carrier with.
You are
Is
modulating the
this
carrier signal.
wait? Is it? Yeah. Where's the message signal? Isn't this is the message signal? Yeah, is it? Or
Correct,
is
correct. So what does the question say? By modulating a 4-volt peak to peak 100 kilohertz carrier with a S of T.
yeah
So they're giving you the
yes
value S.
SOT. So this is the
So
this,
you're
yeah
modulating the carrier with S of T. So what is S of T is message signal. Clear?
message signal. Yeah.
Okay,
Yes.
so let's try to write down this message signal. So here they given S of message not as M of T, as they given S of T, that is fine, which is given as
Yeah.
pi
Yes.
cos 10 raised to 4 pi t,
Yep.
which is given as AM cos 2 pi
2 pi
FMT.
FMT. Yes.
So 10 raised to 4 is equal to pi is equal to 2 pi FMT.
Yep.
Pi gets cancelled, t gets cancelled, pi gets cancelled, t gets cancelled.
Yeah.
Fm is equal to 10 raised to 4
5.
upon 2. Yeah, tell me.
So it's a 5 5 times 10 to the power 4, isn't it? Yeah,
Can I write it as this?
yeah, you can do it. Yeah, absolutely. Well, let me jot this down, it's actually very useful, So, so it's, let's just,
And I hope that you understand in Jerry, right? I'm not teaching you like
yeah, yeah,
as you told me right now that in
yeah,
college everything was just pushed on you.
yes.
So you are in which year right now?
Wait. Yes. So let's go.
Yeah. Okay. So this is what is your S of t. Ideally, yeah, S of t is M of t, but they have denoted as S of t. That is fine. Okay. So and they have given the Kf to be as 1 kilohertz per volt. So the Kf is given as 1 kilohertz per. So now we have jotted down all the given data to us, right? This is always the first
Yes.
step of solving a question there. Okay. Whatever is the data given, write it down in terms of the symbol.
Yes.
Any doubts till here?
Okay. Yes. Okay. Understood.
Sure. Can we move ahead?
Yes. Yes.
Okay.
We can move on. So yes.
Okay. So what is the first question? Maximum frequency deviation. So what did we learn about frequency deviation formula? Your del f is equal to kf into am, right?
Yes.
What is the
Yes.
value of kf? 1 kilohertz per volt into what is the value of am? 1 volt, right? If you see,
Yeah.
is it 1 or is it 5? 5, right?
Yeah.
So it is 5. So it is 5 kilohertz.
Yep.
Any doubts in this, Jerry?
Mhm. Wait. So let me take a look. Again. Sorry. So can you
Yeah.
move up the page? Yeah. So delta F is equals to KFAM.
Mhm.
Okay. Understood, sir. Understood.
Okay. By the way, in which year of engineering you are currently?
Uh, 30 years, sir.
Okay. Now, the next thing that you have is the modulation index.
Okay.
It's given as beta. What did we learn the beta value to be? The formula.
Modulation index. Yes. Wait.
So, so, so del f upon fm.
Yeah. Delta F. Yes.
So what is del f over here?
Delta F is 5.
So it's del f f1 fm. Del f is 5. What is fm?
FM is the frequency modulation, isn't it? FM is 5 as well, isn't it?
What
Yeah.
is beta
Oh,
value
okay.
then?
Wait. Where's the thing? Did I joke down this? I just not. Wait, let me find something. So that I have very weird way. Something weird happened. Ah, it's here. Okay. Okay.
So what
Beta
should be
is
the value of beta b?
it's 1. Hello, sir. Yes, 5 is 1, isn't it? Okay.
Why? Okay.
Excellent.
Okay. Now what is so what kind of frequency modulation technique is this?
This is wide, isn't it? Wideband.
Yeah, wide band pass effect. Okay. The third point is about bandwidth. So bandwidth, I told you is 2 into beta plus 1 into FM,
Yes.
2 into 2 into 5 kilohertz, which is 4 5 are 20 kilohertz. Any doubts in this, Jerry? Any doubts?
Wait. No, it's good, sir. It's good.
Okay. So then next thing is the power of the FMC. Are you able to see this thing? The power of the FMC. Okay. The power of the FMC is given as, again, the value of beta is equal to 1, not 2.41 or 5.5. Hence, I can say AC square by 2R, which is 2 square upon 2 is equal to clear?
Yep.
Okay, so this is about it. So, any doubts in these two numericals?
Not really. Wait. So this is the pre-lab question. Our pre-lab is done.
Yeah. So pre-lab is done. I told you this part is something I am uncertain about. So of course, Jerry, I am also teacher. So of course there will be certain things which even I will be uncertain about. So the one that
Yeah, of course.
I'm uncertain about, so I'll tell that directly, honestly. I will not lie from you. Okay, I'll tell you the truth that this
Okay.
part I know, this part I don't know. Okay, so I
Okay.
like to be very honest. I don't like to lie in this. So maximum
Okay.
part I've taught to you. Okay, is it clear?
Okay.
Any doubts you have? You want me to repeat again all these questions?
So basically bandwidth, but in-hand power ratio and the power of the modulating signal, you are uncertain about it, is it?
Yes.
Oh, okay. Interesting. So have you seen my notes or textbook, or did you investigate any luck with
I
that,
did
or
try. I did try, but I didn't find this other particular thing. Might be that you can
okay.
go through it once. It's something that you can let me know. Okay. Okay.
Okay. So are you gonna
Anything?
further are you going to further study on this, or further investigate on this, or probably you're not gonna
I
do
will
that
try to.
immediately?
I'll try to investigate because I did try about in-band ratio, but this was something that I didn't find. Okay. If you have some notes or
Okay.
something, you can just one time try to go through that in-band ratio. Okay.
Okay.
Okay. Any doubts in the other question, Jerry?
No, really, so good.
Okay. Did you understand what I'm teaching? Should I be changing some technique of mine? I'm going too fast,
No,
too slow,
no,
something like that.
no, not really. So let's get into lab, the lab.
Okay. Now the lab part, if you see over here, I will just be
Uh, s-
solving one particular type over here.
can you check your WhatsApp, Check your WhatsApp. I just sent you 2 pictures of the equipment, Maybe you can take a look. That would be, slightly helpful, If you just like sort of guide me through like how to use the things, maybe, just the important things I need to watch out about. Can you just check your
Uh,
WhatsApp? Yeah,
have
like
you
three
sent to
images.
Aditi on WhatsApp?
Yeah. Check your WhatsApp. Yes, your WhatsApp. I sent to the guy, and then he sent to you. Obviously, you need to check the
Okay,
WhatsApp.
fine. Okay, fine. Let me see. Give me a minute. Give me a minute.
Yeah.
Mm, mm. Hello?
Yes, I'm here.
Yeah. So I did go through this one particular thing, like what is given to you over here.
Yes,
All
and then
this.
the rest is banana cable and then all those things, oscilloscope, you connect those probe together, the
Yeah.
whole thing.
But I highly recommend over here also to you, Jerry, that this is a particular part, right? See, all the parts and all the nodes and modules in this, are are clearly like visible over here. But it is
Yes,
only when you do these things practically that you'll be able to understand better. Okay.
yes,
Even
yes,
for me also, it's when I do it practically, then I understand better. I can teach you the
yes,
theoretical part. I can teach you the concept. But this lab part, is something that you will have to do it by yourself when you do it in the practical. Okay. Because that is something we do practically. What I will do you is that we will take this one question which is over here. Are you able to see this question? This,
yes, yes.
this one? So we'll read this question and then show you how do we actually solve this theoretically. One time. Okay. So that you get an idea. And then obviously when we do practically, that is a deviation in the value. The theoretic value will always
Yes.
differ with the real value a little. Okay. So I'll just show you. But the practical part, Jerry, you'll be able to do it only when you perform in the labs, not when
Yep.
I'm teaching a theoretical. Okay. So please, if you have the PDF, open this part.
Wait. So let me do something really quick.
Yeah.
Let me do something really quick. Uh-huh, 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 uh-huh. Continue working. And then yes.
Hello.
Yeah. So I'm still here. Wait. I just need to connect something and connect to another display. Yeah. Uh, wait. So I'm back. Yes. Okay. So basically, we're
Yeah.
looking at the question, part 4 in
Yeah.
page
So
4.
basically, I will just take up this one question which is over here, explain you theoretically how do we apply
Okay.
this question as a theoretical question, because here it is told in terms of a lab. Okay. But the same question might come to you in your exam as a theoretical question also. Okay. So
Yes.
how do we solve
Yes.
that question? I'll show you. Fine.
Yeah.
So let's try to read the question and let's try to understand what is given in the question.
Yeah.
Okay. The question says over here, the frequency sensitivity of a VCO, voltage control oscillator, is given as 10 kilohertz. So what is frequency sensitivity given as? Kf is equal to 10 kilohertz per volt. Correct?
Mm-hmm.
You can set the free running
Yes.
frequency of VCO to this. Now, what do you understand by this value? What is this value? It is FC, 100 kilohertz.
Wait. So wait. Let me just take this down. Yes. Different pages. Okay. So this is the experimental one. Okay.
Wherein they're saying that the VCO, voltage oscillator, is having a KF, that is the frequency sensitivity of 10 kilohertz, and the
Okay.
setting frequency of VCO is 100 kilohertz. So always remember the free running frequency of a VCO is 100 kilohertz. Always remember this thing. Okay. So if this value is 100 kilohertz initially, so what is it? It is FC, right? We always learn that FC is a very high value and it is 100 kilohertz. Clear?
Oh, okay.
Okay. So then they're giving some additional information that for your lab, then connect 1 volt DC voltage and all those things. That is fine. Read this question. Okay. Modulate the VCO with a 10 kilohertz sinusoidal signal. So what is this, Jerry? Is this M of T? Modulate the VCO with 10 kilohertz sinusoidal signal. That means what? The FM is given as
Modulate is message signal, isn't it? I assume it's message signal because it's quite small. The
hence I'm
frequency
writing
is very
FM as 10 kilohertz. Right?
yes.
Yes. And they're telling that to produce a 4 volt peak to peak FM signal. Now what happens? Here 4 volt peak to peak is not an AC signal. It is a FM signal with beta is equal to 1. If you remember the standard equation, Jerry.
Beta is 1. Okay, so it's a wideband, huh?
Right.
Yes, okay.
Right? So the
Yes,
AC value is, since they are told you for the 4 peak to peak is the FM signal. So the FM signal is 4 volt peak to peak. So it is 4 volt peak to peak by 2 is 2 volts. Is this clear?
Yep.
Yeah. So what happens is, if you see, whatever. Okay. Okay, now this is about display the temporal waveform that you're able to see on the oscilloscope. So this will be a part of your lab. What I want to teach you is this part. Okay. What this telling you is that.
So the first part is done, huh? So is it, I just plug in the numbers, or something? Can you spoon feeding?
Yeah. So when you do the lab part, you'll be able to see the waveforms over there. You just need to sketch those waveforms. Okay.
Okay. So what does the signal going to look like? What do you think it's going to look like?
What are you saying?
What do you think the waveform is going to be look like? Can I just I have my own waveform, so I can just compare it. What do you think the waveform is going to be look like?
Can you come again, please?
What do you think the waveform is going to be look like? Just curious.
Yeah. So the waveforms, if you see, it depends upon the kind of message signal which is there. Okay. If the input message signal is a sinusoidal message signal, imagine.
It is sinusoidal. It's probably sinusoidal, I assume.
Yeah. So if it is a sinusoidal message signal, so what happens? I'll tell you. See, if you have a M of T, right, which is over here.
Yeah. Yes.
And you have the frequency signal.
Yes.
Okay. What did we learn? That the FC, this is the M of T, this is the C of T. What did we learn? That the FC is directly going to be proportional with M of T.
Yes.
So when the frequency increases, so when the message increases, the frequency will increase.
Yep.
And when the message reduces, the frequency will reduce. Again increase. Again, such kind of thing.
Okay.
Are you clear with this? Okay.
Yes.
Of course, depending upon the kind of message, will differ. Hence, I always never prefer to take lab bit explain, because they are depending upon the thing. I always prefer to take the theoretical and the numerical part, because that is something I can teach properly. Okay. So going to this part, just try to understand over here what I'm giving. Okay. It says measure. It tells you over here. Please try to understand the concept properly, what it's telling, so that you get it very well. Measure the 98% power band. So firstly, it is telling measure the 98% power. That means the bandwidth to measure. Okay. So
Okay.
that is, you will do something, over the numeric in terms of the experiment, but we'll try to show it to you in theoretical. Okay. And obviously, then they're telling to find out how many significant sideband components. So the number of sidebands and they're telling you to draw the sketches for the FM signal. If you remember, we had drawn some sketches for FM signal, wideband pass. You remember this part?
Oh, yes. Oh, okay.
So we are going to draw the sketches in terms of the figure, in terms of the data it is given to us. Okay,
Okay.
so we have the sideband, then we have the sketches. So I'll show you for beta is equal to 1. The same thing will be applicable for beta is equal to 2 also. Nothing different.
Oh, yeah. But beta equals to 0.1 is gonna be a narrow band, isn't it? It's gonna be
Exactly. Very good. Very good. I'm happy that Jerry has understood the concept.
I know, sir. You teach well, you know. Yeah, but this is hard, you know. This is very annoying, sir. I know. It's okay, sir.
So
Let's go.
beta is equal to 1. Okay, the first
Yeah.
question says bandwidth. So
Yes.
what is the bandwidth for a wideband pass signal? It is 2 into beta plus 1 into FM. You believe, right?
Yep. Yeah.
Yeah, so the beta is 1, FM is 10 kilohertz. So what can I write? 2 into 2 into 10 kilohertz is 40 kilohertz. Fine. The next thing is number of sidebands. We had done it's the same thing that we have done earlier also. I'm doing nothing different. Agreed?
Okay.
Yeah, please take some
Yeah.
time and try to digest it. If you're not understanding, let me know.
Yes. And number 2, yes, understood. Yes, absolutely.
Okay. This is a number of positive sidebands. If you consider the negative side, it will be 2 into 2, 4, depending upon what is expected. Okay.
Yep.
Generally, as I told you, in real world, right? In real world, no, it is never possible that we have a negative frequency. We always have a positive frequency. So this part that we draw, right, over here, if you see, this part you draw over here, this part, this is just the imaginary part. In
Yes.
real world,
Oh, okay.
only have positive frequencies. Okay.
Yes.
And then the next question is to draw 1 second. Wait, let's just open that one. Give me a minute. Yeah. Give me a minute. Then the next question is to find out the spectrum, right? You have to draw the spectrum. So we'll try to draw the spectrum of. I hope clear, Jerry, things are clear to you. You're not getting bored by my
Yes.
lectures.
No, I'm not getting bored, so it's good.
Yeah. So the next point
Okay.
is to find out the sketch. Okay. How do you find out the sketch?
Sketch, yes.
So what was the number of positive sideband, Jerry? It was 2, right? The number of sideband was 2.
Yes. Yeah. 2. Yes.
So we have FC. So what does the equation say? I'll just tell you the equation. Number part is 2. That is FC plus or minus 2 FM, right? So what will we draw? FC plus FM, FC plus 2 times FM, FC minus FM, FC minus 2 times FM. Any doubts in this, Jerry? Why did we draw this way? Why only 2 and all those things? You can ask me.
No. So it's clear. It's clear. So.
Okay. Now, As I told you last time, this value indicates AC J naught beta by 2. This indicates AC J1 beta by 2. This value indicates AC J2 beta by 2. This indicates AC J minus 1 beta by 2. This we learned in the last class, right, Jerry? AC J minus 2
Yes.
beta by 2. So that's it. What is the value of AC? AC value is 2. So just put that values over here and you will get the graph. Simple.
Oh, okay. Okay, so but the height is different, right? The height is different, you know,
Yeah, yeah.
accordingly
The
is
height
different.
will be different because what property we had learned, Jerry? That when J
Oh,
and
because
beta will keep on reducing as n keeps
yeah,
on increasing.
yep.
So this is the
Yeah, you're
theoretical
right.
part of it. Of course, when we do it, when we do practicing in the lab, there will be certain kind of difference, but this is the theoretical aspect of it. Am I clear to you?
Understood, sir. Understood.
Okay. So now we'll try to do the same thing for beta is equal to uh, 2. Okay. So when beta is equal to 2, sorry, when beta is equal to 2, the bandwidth is equal to 2 into beta plus 1 into Fm,
Yep,
2 into 4 into Fm,
yeah.
8 into 5 kilohertz.
So wait, beta is 2, so it should be 3, right? So it should be
Yeah, it should be. My bad. This 6.
it's a bit
This should be
weird.
30
Okay,
kilohertz.
yes. Sorry, yes.
Okay.
Okay.
I'm sorry for the mistake.
No, it's okay.
Okay. That is very important. And then what is the next thing is that we have number of n. So what is n is equal to beta plus 1 into Fm is equal to 2 into n into Fm. N is equal to
Well,
beta.
wait. 60 kilohertz, and then it's 2 beta plus 1. Mm-hmm. Mm-hmm. Still 3. Okay.
Okay.
Yep.
So now what
And then
difference will happen when we're drawing the spectrum, Jerry? The
so it's
difference will
three
be this.
lines, more line, you know, J3 and then J negative 3.
FC, FC plus Fm, FC
Mm-hmm.
plus 2Fm, and FC plus 3Fm. Because this indicates the number of positive sides. So you have AC J naught beta by 2, AC J1 beta by 2, AC J2 beta by 2, AC J3 beta by 2. 1 second, I'll just confirm once. Give me a minute. I, 1 second. Uh, yeah. So any doubts still here, Jerry?
No, sir.
Any
It's
doubts?
clear. So can we have a break? Can we have a short break, sir? Can we have a short break?
Yes, sure. I was just going to ask.
2 minutes?
I was just going to ask.
Yeah, two minutes,
Yeah,
three
please take a
minutes.
minute break and then. Yeah, fine. Not an issue.
Yeah, we can have a break, sir. We need to have a break. Yeah, thanks. We'll be back in 3 minutes. Yeah, so let's go. Yeah.
Yeah, hello, I'm audible?
Hello, yeah. Yeah, you're audible, yes.
Yeah. So this was the part of it. And imagine they ask you to find out in this case, Jerry, the value of PT. Um, the value of PT. It will be given as PC AC square by 2R. What is the value of AC given as? 2 volts. So 2 square upon 2. This time, Jerry, it's not 1, it is 50. If you see, the R value is given here in the question,
Oh, yes, yes. Hint, yes. Impedance, yes.
right? So depends upon what is given, you can accordingly take the value. Okay.
That's a why,
So this is about,
wait. So can you go back. So go back. Okay, no, can you go back to your PPT, the
yeah,
annotation,
yeah,
the
yeah,
note,
yeah, yeah,
PPT.
yeah, yeah.
Yeah, so basically what you wrote is you wrote PT, so obviously PT is equals to PC, okay. PL or PC? PT is equals to
PC,
PC, okay. PC, so it's AC square and then divided by 2R, so it's 2 square divided by 2 times 50, and then very small numbers,
yeah.
0.4, 0.04. And so now I have a question now. So why do they asking for measure the 98% power bandwidth of the FM signal? Why is that?
Yeah, see, what happens is that, here they're talking in terms of a practical aspect. Okay. Whenever we are doing any of these scenarios, okay, even when we generally also say the bandwidth, right? The
Yes, yes.
bandwidth cannot be, a complete ideal bandwidth. You might have heard that communication is one of the most affected problem. Communication is noise,
Yes, absolutely. Noise.
right? The noise is something that can really distort your entire communication channel. So 98% is something that is considered taking into effect the practical condition.
Okay. But so noise could be more, no? I don't think it's
Yeah,
2%, maybe
but
10%.
hence if you see, what we do, have you ever thought of this question? Why are we, in terms of you, if you see in AM, right? In terms of AM, we should draw the spectrum as a triangle always. FC, FC plus FM, in FC in terms of
Yeah,
AM.
absolutely.
Yeah,
Absolutely.
so why do we do it in terms of an impulse for a FM? Have you ever thought of it? Why do we integrate with the impulse? Because what happens is that more is the bandwidth, more is the chances for noise to enter.
Okay.
That is the reason we always indicate FM in terms of impulse signal.
Okay. Understood.
Okay, now the next part will solve for beta is equal to 0.1. Actually, I thought that this part I leave to you, but then since this is for narrow band pass and we have not solved question on narrow band pass, I wanted to show you one example of narrow band pass. Okay, first solve this question.
Okay.
So
Yeah,
narrow band
probably
pass,
we don't really need to put. We don't need a lot of Indians, I sort of get the idea of wide bypass. I think yeah, we just need to do the narrow bypass. Yes, good.
yeah.
No
So
waste
then
our time on this.
narrow
Good.
band, if you know, the FM is given as band 2 times FM. 2 into FM. What is FM? 10 kilohertz.
Mm-hmm.
So it is
I believe so. Yes, 10 kilohertz, 10 kilo. Yes, correct. FM 10, FC is
20
100,
kilohertz.
and yes. Okay. Wait, let me jog this down, sir. Let me jog this down. Let me jog this down. Oh, wait. Okay, so this is very interesting, because in this case, it's gonna be hello, sir, are you still here?
Yeah, I'm there.
So 2 times 1.1 is 2.2 times 10 to the power of 10 to the power of 3. Okay. So it's 22 kilohertz. Okay. It's
No,
around
no, no.
22.
Again, no,
What
no.
what?
See, what is the bandwidth for narrow bandpass FM? It is 2 times FM, not 2 into beta plus 1 into FM. Hence,
Oh, fuck. Okay.
hence, hence this is the reason
Ayo.
I tried to solve this question here. I didn't tell you only to solve because I knew that this mistake will be done. As soon as you move to narrow bandpass, you should try to remember those set of formulas which are the narrow. I'll show you that.
Oh yeah, the thing is FC plus FM minus FC minus FM. Yes.
See here,
Oh yeah. Oh yeah, the things.
right?
Yes.
Okay, so the next point is after point one, the next point is how do we indicate? Okay, most importantly, how do we indicate the spectrum? That is very important, right? The spectrum, how do we indicate? So if you see here, the spectrum for narrow bandpass is to differ, right? We had something like that. FC, AC by 2, FC plus FM, AC, AC beta by 4. We had AC beta by 4.
Oh yes.
And the same thing reflects over here, right? So the FC value is given as 100 kilohertz. FM value is given as 10 kilohertz. Beta value is 0.1. AC is 2. Just put the values and draw the graph. This is frequency. This is the XFM of T. That is a narrow bandpass signal. Any doubts?
No, sir. Okay, should be good, sir. Should be good.
Yeah.
Let me
So,
just joke this
yeah.
down. Let me joke this down,
Yes,
sir. We
yes,
do
yes.
this
No,
slowly,
no
sir. Yes.
problem. No problem. No problem.
So basically, sir, the modulation is done. So now we're going to move to demodulation, I believe.
Yeah.
And
So basically,
oh
yeah, wait. So
yeah,
basically,
let me draw
one
this,
second.
sir. No, wait.
Yeah, fine. Yeah, you can take the time.
Yeah. Wait, sir. I need to connect something. Wait. My laptop battery is dead, almost dead. Wait. Okay, so let's go. I understood. I have to mirror that as well, mirror, so it's like, negative SC plus FM and then
Yeah.
negative SC plus FM and then, yes. Okay.
So basically now I will teach you the demodulation technique, which is there of PLL. Okay, so I will be closing this particular PDF. What the next topics I'll be teaching you in the next 15-20 minutes will be what is PLL
Demodulation.
for the demodulation technique, which is given diagram over here. I'll explain you in a
Okay.
much better way, okay, so that you understand.
Okay.
It might have been
Okay.
taught you in the college also, but I'll try my best to teach you. Then I will teach you, and I'll teach you some of the theoretical parts wherein we'll compare the performance of narrow band pass FM with wide band pass FM. These two comparison I will do for you. Okay.
Yep.
I will
Yep. Yep.
teach you
Yep.
PLL and teach you this part. With this, I will be done with what I had to teach in terms of your
Demodulation.
frequency modulation. Okay.
Okay.
Okay. After this, there is one more concept of comparison of amplitude modulation, frequency modulation. But since I've only covered frequency modulation, comparing amplitude modulation will be difficult. That is altogether a different concept. If at all we learn amplitude modulation sometime next time, then it makes sense to do the comparison. First, it's important to know amplitude modulation. Compare. Okay? So with this, my assignment will be completed of teaching you the theoretical portion and solving some of the lab questions. Fine?
Yep.
So
Yep.
this will
Yep.
take
Yep. Yep.
hardly 15-20 minutes. And with that, I will be done. Okay?
Yep.
So let's
Yep.
begin.
Sure. Yep.
So I hope till now everything is clear to you. I've not gone too fast, or I hope you have not got bored with me.
No, it's good. Smooth, yeah? Smooth is good.
Paste locked loop PL. This is a technique for demodulation technique, generally for wide band pass. Generally. Okay. So I'll draw the diagram for you.
Okay.
I'll draw the diagram for you. Tell me once you complete drawing the diagram.
Wait. This is like a control system. This is like XFM T. Okay, so it's a phase detection, is it?
Yeah. So it's a phase detector, basically, which acts like a multiplier.
Okay.
So either you draw this way, or either you can draw it with the help of a multiplier also. Any which way is okay. Different books will have different annotations. Please refer what is taught to you so that accordingly you can draw. Okay, but anything is fine. You can draw a multiplier also. You can draw a phase detector also. Anything is fine. The main intention is that the diagram you will get in the books also. I want to explain you the concept.
Okay. LPF, yes. But so LPF and VCO, these are all should be the same, huh?
Yeah. The LPF is the low pass filter. Then there's an amplifier. Then there is a VCO, which is a voltage control oscillator. The carrier frequency of VCO. Okay.
Can we talk a little bit about oscillator, before everything starts? Do you think this is too much for you if I just ask you about, something related with oscillator? So what is an oscillator? Yeah, sometimes I'm still confused. What is oscillator?
See, firstly, the point about, there are two things over here. One is the voltage control oscillator. So the basic point remains, what do you mean, by a oscillator? What is the meaning of an oscillator? Okay.
Yes, and
So
yeah,
what does
we
it
can
do is
maybe talk
that
about it.
so what does it do is that it always gives you certain kind of fluctuations. Yeah.
So
So basically,
oscillator, so a
so what
fluctuation.
do you mean
Okay,
by
so
oscillate?
by
Basically, what is oscillate?
yeah,
Oscillate means
moving,
that it
yeah, moving
gives certain
around, moving around.
fluctuations
Ah,
in a
okay.
periodic manner. Periodic manner. So if you remember, like for example, like we had this clock, right? And we used to have this
Yes.
thing. It used to go here, there. It used to keep on oscillating in a
Yeah.
periodic manner. The oscillator. In terms
Yeah.
of electronics communication, you can just tell that it gives you certain signals in a periodic manner. Of course, there is much more to
Okay. Okay.
say oscillators, but this is just the brief idea of it. Okay. So
Okay.
did you draw the diagram, Jerry? So that I can explain you quickly.
Yes, I have drawn the diagram. Yes.
Okay. So first, let's try to understand what is happening. How is my x fm of t is going to give me my m of t? Okay. So you see here, Jerry, we have a multiplier. Okay. Like we have a multiplier which is having your x fm of t and which has your x naught of t, right? Which I showed you, 1 and 2. It's like a multiplier. So my x
Okay.
fm of t, Jerry, if you remember, we learned one equation, right? I'm sorry, again, I'm going back, but I want you to correlate with what we learned earlier. Okay. If you remember, this is the equation, Jerry. AC cos 2 pi
Yes. Yes.
fct plus phi. So we will
Yes. Yep.
write that equation over here. AC cos 2 pi fct plus phi. And what is your x naught of t given? I'm just writing the equation. Just try to understand. So one is the x fm of t AC cos 2 pi fct plus phi, and x naught of t AC sin 2 pi fct plus theta. That is
Yes. Yes.
very important.
Oh.
So what is happening
Oh.
is that the output of a voltage control oscillator is having a frequency of carrier which is synchronized with the carrier frequency of x fm of t. Is this line clear to
Yeah.
you?
Oh, so basically they synchronize, huh?
Yeah. So both the frequency are same. The output of VCO and the x fm both are same. The phase will differ. It is phi and theta, but the
Oh.
output will
Okay.
remain the same. Fine.
Oh. Okay.
Is it clear?
No. Oh.
Okay.
Okay. Yep.
Okay,
Yep.
now let's try to do some mathematical operations. It's a multiplication, right? So it will be AC square cos 2 pi FCT plus phi and cos and sine. I'm sorry, sine 2 pi FCT plus theta. Correct? If I multiply,
Yep.
okay. So can
Wait.
I
Wait.
write
This
it
is
as
what is this equal to, sir?
equal to which you're saying? Which equal to?
This is what AC squared. This is what? This is your ST, is it? Oh, it's what?
Yeah, no. This is
Oh.
this one. The output of this.
Oh. Okay. Oh. Okay. Okay.
So can I write it as this, Jerry? Tell me if I'm wrong.
Wait, I think you use double angle formula or something. I believe you use all those things, and I'm not sure. Wait.
I've just multiplied here with 2, so I've divided by 2.
Yes, yes. Okay.
Okay. So if you see, sine A plus B plus sine A minus B is equal to 2 sine A cos B. Do you know this expression,
Uh,
Jerry?
oh yes, that was just the formula. Yes, this the I think trigo identity.
Yeah. So can we move ahead or should I wait?
Okay, so can we go to slowly, sir? This part is very annoying
Yeah.
part. Yes,
Fine.
sometimes
Fine.
people make mistake, you know.
Okay. So see what happens is that I have written the basic equation, which is,
Yeah.
multiplying this with this. Okay. I got this first statement. Then I divided this by 2 and I did into 2 to get this 2 sine A cos B. I know that 2 sine A cos B is equal to sine A plus B plus sine A minus B. So what I will be doing is that I'll be breaking this part as sine A plus B and sine A minus B.
Yeah,
Meaning,
yeah, absolutely.
if we square by 2, sine A plus B, that is sine A plus B, that is 4 pi FCT plus theta plus phi plus sine A minus B, theta minus phi. Is this point clear?
Okay.
2 sine A sine B is given as this thing, sine A plus sine A minus.
Yeah.
Clear? That is when passed through a low pass filter. Is this expression clear? Any doubt in 1, 2, 3, 4? I should explain you again.
No, 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 no. It's okay. So, kind of get it. I kind of get it. Yeah. Two
Okay.
pi and then sine,
Now,
sine. Yes, yes, yes. Two cosine. Yeah. So can you move up a little bit? Yes. No, back, back, back. No, up one page. Yep. Mm-hmm. Two sine. Yes. Ah, okay. Yep. Yep. Okay. Sure. I can see. I can see this. So this equation very important. Sine A plus B. This one very important. This trigo identity. I believe it's provided in the formula. But sometimes you need to refer back, refer back, refer back. You get what I'm saying? Sometimes, yeah. Sometimes a trigo
so now
problem
this is
still.
going through a low pass filter, right? Only the
Yeah. Yeah.
low pass will be transmitted. So what happens is that this part doesn't get, only this part will get transmitted. So what I'll have
Oh, really? Why is
is,
why is that?
yeah, I'll tell you. See, this part is going through a low pass filter, correct? Which I showed you over here.
Yep. Yep.
Low pass filter means it will only transmit the lower frequency, not the higher frequency. If you see in this question, we have such a high value of FC, and here there is no frequency. So what do you feel, Jerry? Which one will be transmitted by this or this via low pass?
Excuse me again. I'm sorry. What?
See, when I'm passing through a low pass filter, right? The lower
Yeah. Yeah. Yeah.
frequencies will be transmitted, and the higher will be restricted. Correct?
Yes. Yes. Yes.
So here, this value is 4 pi FC. You know FC is such a high value, always.
Yeah, yeah, yeah. FC is the carrier frequency. Okay, it's very high value. Oh, okay. I get what you're saying. Oh,
So,
okay.
so this part will not be, and only this part will be transmitted. Any doubts in this? You didn't
Yep,
understand? Okay. Clear?
yep, yep.
Okay. Now, Jerry, this is what you will get at the output of low pass filter over here. Now, what is my aim? Is to get M of t. Correct? My aim is to
Yes.
get M of t. Now, how do I get M of t? Jerry, do you agree with this? Do you agree with this statement? Hello.
Yep. Yep.
Why? I
You
give
can see
example.
that.
Sine 0 is 0.
It's 0.
So
Yes.
when theta is
Sine
small,
1. Yep.
when theta is small, theta is always almost the theta is equal, sine theta is almost equal to theta.
Yes.
Hence, can I write it that sine phi sine theta minus phi will be written as theta minus phi if theta minus phi is small?
It becomes negative side, sine negative side.
No,
Hello?
hello.
Wait,
No,
wait.
what am I telling is sine theta minus phi
Oh, okay.
will be equal to theta minus phi if theta
Oh, okay.
minus phi is small, like we had for this.
Okay. Understood.
Okay.
Understood.
Now, when we say na
Yeah.
phase lock loop, why do we say that? Because now see, if I say theta is small, right? Theta minus phi is small. When can I say theta minus phi is small? When my theta is almost equal to phi,
Yep.
right? So this condition is called as the locked condition. Hence we say phase locked loop.
Oh, okay.
This is clear. Now,
Yep.
now what happens is that if you remember, Jerry, long time back, we learned this thing, right? The the phase is always directly proportional to m of t, right? In phase modulation.
Pardon? I beg your pardon again? Sorry, what?
What did we learn in phase modulation? That the phase is directly proportional to m of t, correct?
Yes. Absolutely. Yes.
Yeah. So what happens is that if I've got the phase, that means I've got the m of t also, because directly proportional. That is the
Okay.
way we get m of t through PLL.
Okay.
I will explain you the entire procedure again because it is a little complex. I'll tell you what happens. A
Okay.
phase lock loop is basically for a wide bandpass FM, wherein we have X FM of T, okay, going as the input. We have the phase detector or the multiplier, and we have the output of the voltage control oscillator X naught of T. Okay, this two signal will get multiplied at multiplier. So we have AC cos 2 pi FCT plus phi and AC sin 2 pi FCT plus theta getting multiplied and giving this final value over here, which is over here. Now
Yep.
this part is the part through a low pass filter. So this part get negated out and I only remain with this.
Uh-huh.
Now I can say sine theta minus phi is equal to theta minus phi if theta
Yeah.
minus phi is small,
Uh-huh.
and theta minus phi can only be small when theta is equal to phi, almost equal to phi. And we have learned that phi is directly proportional to m of t. Hence, I can find out
Yeah.
m. This is what phase lock loop uh, process of demodulation is. Any doubts, Jerry?
Oh. Oh, okay. Wait. Oh, that's the whole purpose of POL, is it?
Correct. Just to find out the m of t. Of course, little complex, but if you keep on, that's why I told na Jerry. Today I've taught and gone. I'll teach and
Yeah.
go. But you have write the exam, so you have to keep on revising it. Teaching is just one part of
Yes. No. Yeah. I know, sir. I know about this.
okay.
Active
But
learning, you have to like
yeah, but actually
refer back,
very important.
refresh your
Yeah,
memory.
because see, I just need to teach and go. If you have to write the exam, so please revise properly. Okay, and I've
Yes.
tried my
Yeah,
best to
absolutely.
explain you properly. Okay,
Uh-huh.
and the last topic
Yes,
for
absolutely.
for my lecture is going to be performance comparison of narrow bandpass FM and wide bandpass. Let's try to understand what is the difference and everything. Okay.
Okay.
So the parameter, wide bandpass FM, narrow bandpass FM. Clear? So firstly, I talked about modulation.
Performance. Wait, what is that? So performance CCMP. What is it? Oh, comparison. Okay. I think okay. NBFM and WB wideband. Yes. Okay.
This is range. So please write down till here. Then we'll do the comparison, 4 points, and we'll be done.
Yeah.
Okay. So what is the modulation index? Wide bandpass FM. I taught you beta is greater than or equal to 1. Beta is smaller than 1. Okay.
Yeah. Wait.
The mag
I'm writing it
the
down
maximum,
now.
yeah. The maximum deviation theoretical value for a wide bandpass FM is 75 kilohertz, and here it is around 5 kilohertz. Okay.
Wait. What maximum deviation? Second part is.
Yeah. So since it is a wide bandpass FM, the maximum deviation will be more.
Oh, okay. Yeah, wideband will be more. Yes, absolutely. And frequency range, yeah.
Yeah.
Okay, understood. Okay, what is 4? Number 4, sir. What is number 4?
I'm sorry. Number 4, application.
Application, okay. Okay, entertainment.
Yeah.
So basically, if we are having a Skype meeting or Zoom meeting, we are all using wideband, and then we're talking through phone, like just the normal phone. The call I call you, it's a narrow band.
Yeah, because what happens is that those require less range of frequencies, and these require high range of frequency. So also accordingly, this comparison.
Okay.
So did you note down?
I did wrote down. Yes.
Okay. So with this, Jerry, I am done. So I have completed my assignment. What was given to me, I will provide this PDF.
We still haven't produced the performance comparison between amplitude modulation, frequency modulation. So maybe we can do that in the next session.
Yeah. But for that, basically, why I didn't take that part is that because I have not taught you in depth amplitude modulation. So without that, I cannot do the comparison between amplitude.
Yeah, maybe we can do a lesson about amplitude modulation, maybe tomorrow or whatever. I will contact with you. Maybe we'll do a longer session tomorrow about amplitude modulation. But so I'm very scared that we might, if we do too long, right, we might get overloaded and then saturated and then all those things. So it's
So see, what I have done is that I have completed my, other task that was given to me about frequency modulation, and I've covered the complete theoretical aspects and this thing. So Jerry, what I like to tell you is that you might have understood from my lectures and everything. I mostly like to take the theoretical part of it and some numericals. The lab part is something that I cannot handle because that is to be done in the lab. Okay. Apart from that,
Yeah,
I'll try
yeah,
to
yeah,
teach you everything. So this is the part that I've
yeah,
covered from the PDF and this. So I've completed my assignment.
yeah,
Now,
yeah.
if you so did you have any issue with my teaching or anything you didn't like or any problem or
No,
anything?
no. That's okay. It's okay. So we just need to plan our what's our next stage. You get what I'm saying? It's like planning ahead. We're gonna do next time. We're gonna do whatever.
Okay, so
You
do
get
you
what I'm
want to
saying?
continue
That's
lectures with me?
maybe we can do a little bit of amplitude modulation. Make me enhance knowledge in terms of amplitude modulation. I'll send you some of my notes about amplitude. Did you get my notes on amplitude modulation, or it's not yet?
Yes.
Or it's kind of
I
thing.
wait. Let me open the amplitude modulation part. Let me
Yeah.
just a minute.
Did you
Just a
did you
minute.
get PPT or those things, lost in translation, sometimes these kind of things occur.
1 second. 1 second. Just give me a minute. Yeah. Just give me
Because
a
the
minute.
lecture slide, it's the first 2 weeks is about you know the first 2 weeks is about and then next week this week next week and this week we have a random process, power spectral velocity, all those things, annoying things again, yes, all those things, yes.
Okay, so so with this I've completed frequency modulation part. Okay.
Okay.
My humble request to you will be if you want me to take any topic, okay, firstly, let Aditya know, okay,
Okay.
because then
Okay.
I will have to decide whether I know that topic or not. If I know that
Okay.
topic, I'll require some time for the preparation. I'll
Yes,
prepare
yes.
and I'll teach you. If I don't know, then
Yeah.
I'll say I don't know. Okay.
Yeah. Okay. But random process, power spectral density, and noise, these should be fine, right? Noise performance and analog modulation of noise performance of analog modulation, this should be fine as well, is it?
1 second, let me go through that because actually I can teach random process. Power spectral density I'm
Okay.
not aware about. So I cannot teach that part, but I can teach random process.
Oh, really? So power spectral density, not very good at that, are you?
No. I'm not good at that. That's very honest. I will just like to show you
Okay.
something. Okay, 1 second. Are you able to see my screen?
Yes.
Yeah. So I have been teaching random signal analysis. Okay, for a particular
Okay.
student in India. Okay,
Okay.
and if you see, I have taught and I give this note to the students. You able to see this thing
Okay.
over here?
Yeah. Yes.
See, I have taught all the problems and everything in random signal analysis. Fast
Okay.
I've never done, but random processes and everything I have taught. If you see, I give my notes and
Okay.
everything. What is probability?
Yeah.
I'll just show you one
So
specific example.
no. I understood about it. So probably I'll ask the guy, to refer me to somebody else. It's okay, sir. It's okay. I just because I enjoy what you teach, so it's like, maybe we can, go further with this, but it's okay. Yeah, we can talk about it later on. Yeah, maybe you can teach me about amplitude modulation. It's okay, sir. Yeah.
Okay,
I'll talk to you
okay.
soon. Yeah.
Okay. So about
Uh,
amplitude modulation or something, if you want, because I told you I can give you a session on the theoretical and some of the numerical part, not on the lab part.
yeah.
Okay. So
Yeah. But
so
no. So do you can do some, you can, like, how to do some of my workshop question. I think the very difficult workshop question. I'll probably will send to you as
actually,
well, and then you probably go through it. I
actually,
have a
actually,
solution.
yeah,
Actually,
do you have
what?
solution?
I do have a solution. Why is that? No, but it's very unclear solution sometimes. Yeah, and I think one of the solution they make the mistake. So I'll probably send you the updated version. Yeah. Why so?
1 second, 1 second. So you are saying that you have the assignment questions and the solution both.
No. That's for workshop questions. That's like tutorial questions. So it's like they discuss in tutorial class, and then it's more challenging question, and then maybe we can go through some of that as well. I'll send you that, and then we can go
Okay.
through that. Yeah, I will
Okay,
send
just
you
do
the.
one thing. Communicate with Aditya, sir, whatever you
Okay.
want to. Okay. If I'm
Yes.
comfortable with that, we can have a lecture. If not, I'll tell. I'm not comfortable with that. Okay.
Yeah. Yeah. Okay.
That's
No,
fine.
that will be it.
Okay,
Yeah.
so I have taught the complete frequency modulation techniques to you on theoretical part as well as the numerical part, and I hope that you have understood, Jerry. I've tried my best.
Yeah.
I just wanted
Yes.
that before after the lecture you should be in a better condition because when you told me yesterday that you don't understand these things very well, I wanted to teach you very
Yes.
properly, and I hope that you
Yes.
understood
Yes.
concept.
Yes, yes. So you've been very helpful, sir. Thank you. But I know there's everyone has a limit, you know. It's just you're not very comfortable with the certain part. Yeah, I understand, sir. Thank you, sir. Thank you.
All the
For
best.
everything you did.
God bless. And please,
Yeah.
if you want me to teach something, please let me know little in advance because even I need to prepare and then teach you if you want.
Yes. Thank you, sir.
Thank you so much. God bless.
God bless you as well. Bye. Can you end this meeting, please? Thank you.
Aditya will be ending it. You can drop out.
Yeah. Okay.
आदित्य मैं भी ड्रॉप आउट हो रहा हूँ ठीक है
हेलो
हाँ हेलो आदित्य
ठीक है